I was just curious on what your exam format is.
Yeah, I get a lot of people ask that. I don't think I put it in very well. On the July the 20th, I believe it's the July 20th, it's on the syllabus. On a Monday, you'll get your midterm, and then on the last day of class, you get your final. It will be on WebAssign in the same way that it's like an exam homework. There will be quite major differences. First one is you only get one guess, so it's not like you get 3 shots before it's finished. You won't know whether you're right or wrong, and you won't get any help features. It's timed, so it'll be 3 hours, and it'll take place essentially, I think it's going to be from like 7 to 10.
Okay,
Um,
so
what else? Oh yeah, and there's one very important thing I didn't mention. This, your exam, both of the midterm and your final, I need to see you're working. So when we get closer to the time, we'll explain there's a piece of software. So I'm assuming you all have access to a cell phone, or at least a printer that can print some out, or the mail, I guess, would be the last resort if nothing else works. And I will see you working. And so you will actually write down how you got the answers. Now, in virtually all questions, with a few minor exceptions, there's a fair amount of working that you need to do just to tell me the answer's 42. And do any of you know the connection with the number 42? Come on, if you're a sci-fi fan, you should know 42. Does anybody know where it comes from?
It's the meaning of life.
Correct. Hitchhiker's Guide to the Galaxy. I like that number. So if you, the movie wasn't that good, but if you get a chance, go online and find the 6-part British, it's quite old now, British TV series that is the same thing. It's really funny. So when you have spare time, that's a suggestion. Okay, time to get started. Well, we are about to start a totally new topic, which is kind of nice. I think we've left behind what for most of you is going to be the easiest chapter that you're going to do in this thing. So, and things are going to get, for many of you, it's going to get a little bit more difficult. And then the last section that we're going to do, which is sequences and series, will probably be the hardest one for everyone. So there's a kind of flow to this. Well, I'm going to set up the whiteboard, hopefully, and we'll have a look at what the heck's going on. We're going to look at things called space curves. A space curve is essentially a curve in 3 dimensions. So imagine that's my x-axis, imagine this is our y-axis, and imagine this is your z-axis. A space curve could be something like this, which is called a helix. Now, a couple of things about a space curve that you don't normally get in the old 2D world is that space curves have an orientation. And what that means is that you travel along the curve in one particular direction. In this particular direction, we are spiraling upwards, and that's called the orientation. And space curves are almost always written in this general format. If I write it down as a vector function, then the position vector of the point at time t is given by 3 isolated functions. And by that I mean they have no connection with each other, they are totally independent. So for instance, this could be cosine t, this could be sine t, and this could be 0.1 t. In fact, that particular one would generate a helix not unlike this ship. So can you imagine that you plug in 0, what you will get, let's do that. So at time equals 0, you will get the position of the object, the position vector. But position vector and coordinates are virtually synonymous, right? So if the position vector is funny bracket 1, 2, 3, funny bracket, it's also the coordinates curve bracket 1, 2, 3, right? So they're totally the same thing, really. Cosine is 0, sine is 0, nothing 0.10. So this moving object, space curves are very often thought of as the path a moving object makes in 3D space. This moving object at time 0 is at position 1, 0, 0. Can you imagine? That would be there, right? And then you could find its position at any other point you like. Its position at roughly 3.1 seconds would be the cosine of pi, which is, what's that? Cosine of 0 goes -1. Sine of pi is still 0, and nothing 0.1 pi. So you can imagine that this object has moved to somewhere over here, probably. So be comfortable about what I mean by a space curve. I'm basically talking about a curve in 3 dimensions that has an orientation that is described by 3 separate functions of t, f, g, and h. Now, these are very variable. You could do almost anything. So I'm going to have a little bit of fun here because we don't always get a lot of chance of doing this. So you hold on just for a second. Where are you? Oh, darn it, I thought I'd done it. Never mind, we can still do it. Are you looking at Calc Plot 3D? You probably aren't. Can you see the Calc Plot 3D on yours? You are?
Yep.
Good grief. There is a surprise. It worked. Okay, so I'm going to go over here and I am going to pick space curve. So it makes it life easier. And they've got a pre-built one. So let's see what that pre-built one looks like. X is cosine t, y is sine t, and z is 0.1 t. That was the one I've got in my notes, right? If I click on this, can you see our space curve? Now, this particular one doesn't have arrows, so I guess I'm going to put in 1 there and see if that helps. Yeah. You'll have to trust me, this one spirals upwards, right? You can actually put negative values of t, and you can actually find out where the space, where the curve is at -1 and t is -21 and whatever. Now, if I orientate it a little bit, do you see that if you're on the z-axis and looking downwards, do you see that that's basically a circle? So a helix is a circle that kind of spirals upwards, right? And you can change, oops, you're doing that orientation thing, aren't you? Stop that. You can change these guys to anything. Suppose I change this to nothing 0.2 t. There. Now, it might look like a spiral until you do this. Do you see that this is essentially a diagonal? Kind of zoomy, I'll stop that, darn, that's the thing I hate about this. Can you see in this orientation, it's basically just a sine function? On this orientation here, do you see it's, if you were looking at it at a very special angle, there, gotcha. Can you see all you would see is this line bouncing upwards and downwards if you were standing at that particular orientation? So can you see space curve can have a variety of shapes to them. I'll try changing this guy to t². And we'll see what happens this time. Come on, go away, come back. There we go. Oh, a kind of boring quadratic curve in 3D. you see it? Quadratic curve. There you go. You see it? Now, actually, that is not too bad. Can you imagine you're trying to model an asteroid or a planet or whatever it was, some celestial body, and you put the sun at the origin, which would be a reasonable, in our world, right, would be a reasonable way to do a coordinate system. Can you imagine that if you have enough data, you could plug it into a computer and it would actually predict the pathway of the asteroid? This poor asteroid, it looks like it's going to go through the origin, so it would actually crash into the sun, but it wouldn't take much for me to move it a little bit out of the way. There you go. Can you see one of them coming and paying a little visit and then zooming off again? So you can actually model the pathway of objects in 3D space. Can you imagine, and I'm sure they've got this, I have no evidence, but I'm sure if they don't, they should have it. Can you imagine that you could have intelligent radar? Now what the radar does is it picks up the location of an object in real time. It plugs it into a computer, and the computer, only after knowing a few of its positional points, could put the best fitting curve through it, and you could make a reasonable judgment call on what the future pathway of that aircraft would be, and therefore send your missile out to arrive at where it's going to be and not where it is. Because you know, when you shoot at things, you can't shoot at where they are, because by the time the missile gets to where they are, they're somewhere else. So what you really want to do, if it's not an intelligent one that follows it, don't you want to shoot it to be where it's going to be, so that when the missile arrives, so does the object you're trying to hit. So if that's actually the case, don't share that, because it is probably a secret. But kind of cool, isn't it? That you can, on software, model space curves. And there is a couple of homework questions where all you're going to do is go to that program, plug in the space curves equation, and then you get like a picture, or whatever it is, you get a choice of 4 pictures and you pick the one that looks like it. So that part should be pretty cool. So pretty reasonable way of how do you deal with a curve in 3D space. And Travis, you have a question. What's up?
Does something like a helix have like a handedness in 3 space? Like it could twist one way or the other?
Yes, the way that it, yeah, like a corkscrew, there's a left and the right corkscrew, yes. It also has an orientation, so you either spiral up the thing or you spiral down the thing. But actually, you can adjust the helix. Do you know the helix that I've got here? The cosine and the sine, that's the 2 things that make the helix do. See, if you take this out, these 2 here make a circle, right? That's why when we looked at it in one of the Z's looking downwards. But if you rearrange the position of the cosine and the sine, and you did, for instance, this space curve, I can tell you very roughly what that space curve is going to look like. Do you see how the x and the y values of the sine and cosine? That means the x and y values, not the x and y, the y and z values, okay, right? The y and z values are where the circle's going to arm, and this here is the x. So I would know that, can you imagine a spiral going along the x-axis? So, and does it have a left and right handedness? Yes. Do you know if you switch these 2 things around, you'll make a, I don't know which one's a left-hand corkscrew and which is the right-hand corkscrew, or I guess you could say right-handed helix and left-handed helix, but that's all you need to do. Cool question. Are we comfortable with space curves, how they work, how they're able to describe any curve you like in 3D space? Any questions about that, or can we call that good? Right, let's look at some more stuff to do with space curves then. You remember in 141, I know it's a while back, but we talked about the domain of a function. Now, in the 2D world, if I give you that function, its domain, you say it in English, is described as the usable values of x. Great. And in this particular case then, the domain would be values of x that are greater than or equal to 1. So that's one way to write the domain. This is set builder notation. Much more convenient form would be that. We ringing some bells there. Do you remember doing things like that? Right. So the domain of a 2D function are the usable values of x. So basically, if you sketch this function, you would only get a picture from x equals 1 onwards. It would probably look something like that. So we're going to look at the domain of a space curve. Well, what is its domain? Its domain is the usable values t. Because isn't a space curve really only got one variable? It's called t, right? You know, the first term's t squared, the second term's 2t, the third term's sine t, but they're all t's, and they represent the same variable. So usable values of t. So here's a space curve, and we'll go through a few variations in the theme. Pretty boring space curve. Do you know that would just be some kind of curvy curve zooming off into space? It would probably go in the z direction a lot quicker than the other two directions. In this case, what are the usable values of t for this function? I think I can see you. Yeah, say again.
All reals?
Yeah, so all real numbers. Or if you want to, you could use that notation, right? Okay, let's put some problems. Right, let's look at this space curve. Not a very pretty space curve, right? I mean, I could put it in, and we don't have time, but I could put it in, we could have a look at it. I don't think it would be that interesting. It'd just be a boring kind of look, my guesstimate is. But it does have problems. And what makes domains of space curves a little bit different than domain of good old-fashioned 142 functions, like 2D functions, is that we have to look at each component, the x, the y, and the z, individually, and then we have to combine them into a single relationship, a single restriction on t. So let's take the first one. Would you agree that you can use anybody you like? So all real numbers works for t cubed. What works for the square root of t plus 1? What must be true if you're going to use it?
Any t that's bigger than -1.
You're allowed to equal it as well, aren't you, in this case? Right?
Mm-hmm.
What's the problem with 1 over t?
Any number that does not equal 0. Any t that does not equal 0.
No, you said it fine. I like the way you said it. So what I have to do is combine this. So if I was going to combine this, I'm going to use interval notation because I think that's a little bit easier to see what's going on. You could say it in English. I want t to be greater than or equal to -1, but it's not allowed to be 0. Right? That would essentially be the domain, right? All values of t that are greater than or equal to -1 but you're not allowed to use 0. So that would look something like this. -1 up to 0, can't use me, union 0 to infinity. Does that make sense? And we go with how you find the domain. Right. Okay, let's up the ante to, I'm just trying to think of the ugliest thing I can think of and see what the heck we get. I need something else here. Okay, that's a pretty weird space curve. And we're still going to try and find out what its domain is. So we'll start with e to the power of 1 over t. The 1 over t is the issue. Would you agree it's another situation where you can use anything you like, but you can't use 0? What about t over t minus 1? What's the domain restrictions on that? Agreed?
T can't be 1.
Yeah. Now, the messy one is the square root of t squared minus 9. The usable values in this situation.
T can't be equal, or T can't be in between -3 and 3.
Yeah, it's kind of hard to say, but I know exactly what you want. Isn't it? It has to be greater than or equal to 3, and it also can be less than or equal to -3, but it can't be any number between them. So I'm writing it down, maybe not in the convenient format, but now I have to put all of this together. I'm going to draw a number line, not that you ever need to, but since I'm a visual learner, it kind of helps my brain. I'm going to use some colors. Right. If I use this restriction, don't I have to start here and go all the way that way? And I can use numbers for t that start here and go all the way that way. So that would be this restriction. And then I say, you can't use 1. Well, I was never going to use 1 because of this restriction, so that really didn't make any effect. And this one here says you can't use 0, but again, I was never going to use 0 when I put this restriction in. So in fact, the domain in this case is just all numbers less than -3 and all numbers for t greater than 3. Right, we are continuing, well, maybe not continuing, that's the wrong phrase. Are we happy with how to calculate the domain of a space curve? It's really just doing this stuff 3 times and then combining the result, right? So you don't really need to overthink it too much, because it's using a skill that you've probably picked up from 141 when you were doing domains of just f of x's. So what we're going to do now is do a Calc 1 thing. Can you remember in Calc 1, we did limits. So in Calc 1, you might, for instance, find the limit as x tends to 0 of sine x over x. You remember doing things like that? Now, there are essentially 3 strategies for finding limits. The most likely one, in other words, one that you'll spend is that one called L'Hopital. Can you remember it? Or L'Hospital, as I tend to call it. And what that says is that if you want to find the limit of this as x tends to 0, provided this is in indeterminate form, you can differentiate the top and bottom, and you can find this new limit, and its answer will be the same as the original. So in this case, it's the cosine of 0 over 1, that's 1 over 1. So in this case, the answer would be 1. Indeterminate form is important for L'Hopital. What that means is that if you plug 0 in here, the top is 0 and the bottom is 0. So you're essentially, right now, if I try to do that, the answer that I would be working with is 0 over 0. You see, that's a problem. You can't really evaluate 0 over 0. But L'Hopital, really clever fella, figured out that this limit would generate the same result. You remember that technique? Right. Now, I said there's two other techniques. The second technique is called factor and cancel. So basically, you take the top thing and factor it, you take the bottom thing and factor it, you cancel out some terms, and then you can plug x equals 1 or 0 and get your answer. And the third one I call brute force. The third one, brute force, is typically used when the limit is the limit at infinity. So, for instance, if you were going to find the limit of this expression here, what you can do is you adjust the original question, the original fraction. And you've probably seen, although it may not have been written this way, the trick that you divide the top and bottom by, in this case, x squared. And so the question becomes the limit as x tends to infinity of 1 plus 1 over x squared. That gets you 2. The middle term gets you 1 over x when you divide it by x squared, and the last term gets you that. Now, although this looks quite different from that, and that this looks a lot uglier than that, this is actually a much more useful version for the limit. Because what you then do is you basically do brute force, you plug in infinity. So if I plug in infinity, I get 1 plus 1 over infinity squared. I get 2 plus 1 over infinity, take away 1 over infinity squared. Do you notice I don't write infinity squared because infinity squared is still infinite?
Innocent. Yeah. It's just going to be 0.
Yeah, and that guy's going to be 0, and those, yeah, that's going to be 0, and those two guys are going to be 0. So what you end up with is a half. And that's a very common technique for limits as x tends to infinity and limits as x tends to negative infinity. Again, does it look familiar? How you find limits. So that is the Calc 1 world, right? That's where you probably learnt that. So we're going to use that same process to find the limit. Oh, I got x's there in my brain. Let's try it again. Let's find the limit as t tends to 1. And the function we're going to do it to is, I'll do it in this format, of t plus 1, t squared minus 1 over t minus 1. And I don't really know, square root of t minus 1, there. Now, how do you think you find the limit of this, which is basically the r of t, the space curve?
You just do a limit for each one of them?
Yes. Isn't that intuitively nice? That's kind of what, if you were the first person that came across that problem, isn't that what you hope to be true, right? You don't want anything weird where you have to do stuff. So basically, you find the limit as t tends to 1 of that guy. And you find the limit as t tends to 1 of this guy. And then you find the limit as t tends to 1 of this guy. And then you have to make a decision. not every limit is going to be a problem. Aren't many limits just the value of the expression at that point? So isn't the limit as t tends to 1 of t plus 1 just 2?
Yeah.
Right, this guy in the middle. I could do this by factoring cancel. I could do this using L'Hopital. And can you trust me right now? You can check it out later, it's 2. And this fella here, isn't this basically, you can just plug in the value of 1 and square root of 0 gets you 0. And there is your limit to a space curve. So as time approaches 1, this space curve will approach that point. Now, in the 2D world, you might have a function that has a hole in it. You remember seeing those ones? That might well be x squared minus 1 over x minus 1, right? It has a hole at 1, right? Space curves can have that same feature. Can you imagine that you've got a space curve and at t equals 1, there's a little hole, but that hole has coordinates 2, 2, 0, right? So it has the same kind of, a limit only tells you what the function is trying to become. It doesn't mean that the function actually exists at that point. This space curve does not exist at t equals 1. Its limit is this. The value of the middle term is 2, but it doesn't exist because at t equals 1, don't you get 0 over 0 as a calculation? And 0 over 0 is called undefined, right? Does not exist, can't be used if you want to go through those kind of terms. So that ends up making a hole in your space curve. So the 2D world has transferred into the 3D world pretty smoothly. Agreed? Limits, at least, seem to be our friends. They don't seem to be doing them significantly different. So let's look at another thing that space curves do. So, how do you find where a space curve intersects a surface? Well, let's suppose I have a space curve. Here's a question. What would that look like in 3D? What would that look like in 3D?
A line.
That would be a line, right?
It'd be a line. It's basically made up of 3 lines, but can you see the transition between 2 and 3 dimensions, right? That's a straight line. So can you imagine this pen is my straight line, okay? So let's find out where this space curve meets up with 3x plus 2y plus 4z equals 10. Now, if I was visualizing that, do you recognize the equation of this represents a plane? Remember yesterday? Flat piece of paper. This is a straight line. Can you imagine a straight line meeting up with a plane? One of it possible things is that it intersects with it, right? Would you agree that the geometry says that if a pencil or a pen hits a paper, doesn't only hit it at one point and then they never have a chance to meet up again? The paper isn't going to be bent and the pen isn't like to, change direction. So in this particular case, I know there's only be one solution. I guess the question is then, how do we find that one point, if it exists? Because it could be you know, I'm flying over the top, right? I'm parallel to the plane, right? How do we find that one point?
It's where each of the x, y, and z coordinates equal with themselves. So the 2 plus 3t would have to equal 3, the 1 minus t equals 2, and the 4 plus 2t equals 4.
Not quite, but you're very close.
They would all have to equal 10 when combined, right?
Yes, so the x gets replaced by this, the y gets replaced by that, the z gets replaced by that. That's what my little arrows are trying to show, and the whole thing equals 10. So that would be 3 lots of the x component plus 2 lots of the y component plus 4 lots of the z component equals 10. So essentially, think substitution. Right, now, this is probably going to be ridiculous numbers, but we can do it. 6 plus 6t, 2 take away 2t, 16 plus 8t equals 10.
That first one's 9t, by the way.
What's 19?
The 6 plus 6t should be 6 plus 9t.
Oh, did you all catch that deliberate mistake?
Early in the morning.
Right, I'm glad someone's awake. There's 8, that's 24, and that's 7, and that's going to be 15. And that's going to get me 15t equals negative 14. I did promise you a really ugly answer, but that's negative 4/15. Okay, now, I'm not going to finish this off, I'll just talk it through. If we know that the place where the line meets up with the plane has a t value of that, if you were being asked to find the coordinates, don't you plug this ugly fraction in here, and in here, and that'll tell you, you know, 4, 3, 2. You know, it'll tell you the position vector, which is what the coordinate is anyway. So as a algebraic process, if you want to find out where a space curve meets up with a plane, don't you just do substitution? The x gets replaced by this component, the y with that, the z with that, and then you're typically going to have a linear or maybe a quadratic equation to solve. So I'm going to try, and I'm probably going to fail, but I'm going to try anyway. To do a helix and meeting up with this object. Now, we know what the helix looks like. The guy that's not sine or cosine tells you the orientation of the helix. So can you imagine that this shape is going to be a helix going up or down the z-axis? What surface does this generate?
Going to be a curve, right? Like a curved plane.
It is very curved. Curve it on itself and go round the other side.
A sphere?
It's a sphere, surface of a sphere, which is curved.
Oh, well, yeah, half right.
Okay. Now, making no attempt to be accurate, can you imagine I've got a sphere and the spiral is going through it? Can you imagine that the spiral may well intersect with the surface of the sphere in more than one location, right? So that it could be 2, it could be 1. If the spiral's big enough, won't it actually miss the sphere entirely, in which case it'll be a very big sphere and a very small, a very big helix and a very small sphere. So the answer might be 0. The answer might be 1 or 2 or 3, or who knows how many. Answer might be 1. Well, let's do the substitution part. Sine squared t, cos squared t plus 2t squared equals 1. Now, hopefully this is so obvious that I don't need to ask it, but I'm going to ask it anyway. Is there anything on the left-hand side that can be simplified in some way to make this process a lot nicer?
Sine squared, cosine squared together is 1, right?
Yeah. So in this case, there's only one solution. So what that tells me is that this helix will intersect with this surface of a sphere only at the point when t is 0. So let's find out where that point is by getting its position vector. Sine is 0, cosine is 0, 2 times 0, which is the point 0, 1, 0. Now, can you imagine in a different world, in a different combination, we might have 2 answers here, right? Or 4 answers, or who knows how many. So if I give you a space curve, and I give you some surface, and do you feel comfortable you could answer the question, where, if anywhere, does the space curve intersect with the surface? Right. So we're not using new algebra. We're really just using substitution, and solving whatever comes out of that. I think things are going pretty good right now. We don't have any major what the heck is that about. At least that's what that's the visual faces that I'm getting. Anybody got a question before we have a look at some of the homework questions? Have you got your thinking face on, Lee? Leah, I should say. Is that what your thinking face looks like?
Yeah, pretty much. This is my
Okay.
trying to wake up face.
Okay, so it has multi-purposes, right? It can be used for more than one thing.
Yep.
Okay, I'm going to do this here. Where in heck are you hiding? Ah, you're hiding here, I think. Okay, hopefully you lot are looking at the homework from 3-1. Does that look great? Okay, so I'm just going to talk through some of these guys. In question 1, can you see you're being asked to find the limits of various expressions? They're not using my funny brackets. You see they're using the IJK notation. It's the same thing, right? And so I'm assuming that since it's written in this form, shouldn't your answer be things like 2i minus 3j plus a half k? You know, that kind of look to it, if that's what the result was. Now, if you were doing question 2, do you see that there are 4 straight lines? And this is the space curve. So what I would do is I'd go to that software and I'd put the space curve in. The problem is that, let's just say for argument's sake that it looks like this guy. Won't it also look like that guy? So we have a choice here. Is the orientation going down the way? Is the orientation going up the way? And since I haven't found a way to make that software put an arrow in it, we have to kind of improvise. So I would probably do something like this. Find out where it is at t equals 0. Find out where it is at t equals 1. And won't that give you an idea if it's going uphill or downhill, right? So at t equals 0, won't this be at position 0, 3, 0? Right, so 0, 3, 0 would be here. Do you see where my mouse is pointing? Okay. Now, where would it be at time 1? It would be at position 1, 2, 1. Right, you imagine going 1, 2, 1. Oh, you're going uphill. Right, 1 along 2 and 1. So going uphill It'll be that one. Now, somebody says it might have been these two, in which case, you know, you choose it. But we're just trying to say, you'll use the software to decide what the picture is. If there's two guys, you then have to improvise to figure out which orientation. Now, I guess you could guess, and then when it tells you you're wrong, you guess the other one. But that's not going to help you in a test, is it? Because in a test, you're going to have you won't be given two choices. So you have to kind of have a way of coming across this. Here we have some helixes. The good news about this is that none of the helixes are quite the same as the others. So hopefully when you plug that in, you should be able to tell. I can tell you something just looking at the formula. Do you notice how you've got a sine and a cosine here? Which are in positions, what, y and z? And isn't the non-sine cosine in x? Doesn't that mean the helix should travel along the x-axis? So that means it has to be either this picture here, right, or this one here. So far, so good. If this was sine t and this was cosine t, you would get a perfect circle if you looked along the x-axis. But since it's a sine and a 2 sine, won't that elongate it into an elliptical shape? So I would bet money that even without the software, it would be the fourth one. So sometimes you can actually just bypass. In fact, if you knew that, do you know it takes you 30 seconds to answer that question? There's virtually nothing that you would need to do. Right. Question 4. Here are 2 points. Find the vector equation, find the parametric equation. The vector equation, this is, now that I've seen this question, I now know what the heck they're after. Let's just say that the question was 2t, t, 3t, right? They want you to say 2ti plus 3tj plus 4tk, right? They want you to put an I, a j, and a k in it. And in this question here, they want you to do 2t, 3t, 4t. Right, so it's essentially the same question. Do we all know how to find the equation of a line in 3D space? Remember we did it? You find the vector joining P to Q, that's going to be the V, right, your direction vector. And then don't you just do x naught plus AT, y naught plus BT, and z naught plus CT? And who do you use for x, y, and z naught? I would strongly suggest that you use P. Just in case that's the one they want. Couldn't you theoretically, nothing wrong with it, couldn't you have used Q as your x naught, y naught, z naught? But can you see if you do that, it would be a different looking equation, wouldn't it? And the software might not know that version. I mean, it can only look at the things it's been programmed to pay attention to, and it may not. So I would suggest strongly to always use P. Question 5 is quite fun. You can plug it into the software, right? You could certainly plug it into the software, or you could have an inspired guess. Right? Here are 6 pictures. Only one of them matches this space curve. This space curve right now is being written in what's called its parametric form, right? It's just been written as x is this, y is that, and z is that, which is totally fine. Any suggestions for which one of those 6 it is?
It's going to be a spiral on the XZ plane.
Or a spiral
Sure,
that's traveling
it's,
in the y-axis direction?
There we
Yeah.
go.
Pretty,
Yeah.
pretty sure it's the
First
top left one because it's
I
a
agree.
spiral along the y-axis that grows with t getting bigger.
Yeah, we all agree on that. We may phrase it differently, but me personally, I just say it's a kind of, I call them all helixes. Some helixes are circular, some are elliptical, and some like this one just get bigger and bigger, but they're all helixes of different kinds. So my brain would be saying, oh yeah, you're a helix and you're going in the y direction, you know, the y-axis. And as long as there's only one helix doing that, you're pretty much good to go, aren't you? Now, I'm pausing here because, damn it, it's hard for me to do this. Can someone check the comments in case someone has been typing a question? I have to go out and in, and it's hard for me to do it.
They're just joking around.
Tell them to stop joking around then. You're not allowed to have fun in math. You know that. So stop doing it. Start being miserable, right? No, math is magic. Okay, there's a really weird one. I'll just let you play with them. I don't want to give it too much shows away. Right. Here is some of those intersection questions, right? Here's the space curve. Here's the surface. Right, you remember substitution is the key here. Evidently, there's two answers. You know, t equals 0 and t equals 5 or something. The smaller t, you put the coordinates there, right? It's 1, 2, 3, and the bigger t, you put 12, nothing, minus 10, whatever you get. Here's a helix making an intersection with a sphere. Evidently, in this case, there's going to be two. And now I've just discovered something that's new. Can you imagine two surfaces intersecting with each other? Now, the one I'm not going to do, can you imagine when two planes meet up, they can meet up on the equation, and they meet up as a straight line. So you can imagine the question would be, and what would happen in that case, right? Let's do x squared plus y squared plus z squared equals 9. Do you all recognize that as the surface of a sphere radius 3? And let's do x plus y plus z. Fingers crossed. I'm trying to think of a number that's going to work. I'll do 1. I may end up changing this number later on. But essentially, can you imagine a plane and a sphere? If I've done these badly, won't they miss each other? But if I've chosen the numbers better, can you imagine what's going to happen is that a sphere being cut by a plane, won't you end up with a circle as the intersection? So that's what I'm hoping to get out of this. So here's the puzzle. So I'll redo it over here now that I've got the question. We need to find out what does that guy look like? Okay. Oh, I got a better idea. Yeah, much better idea. I've changed my plane just to be x plus y equals 1. Do you know that'll do a vertical cut? That'll give me nicer numbers. So I've just bent the rules a little bit. Okay. So here goes. I am going to begin by making x equals t. Quite arbitrary, but I decided to do it. I'm going to call this equation 1. I'm going to call this equation 2. Now, if you use the fact that x equals t, and you put it, or you use it in equation 2, it used to be that x plus y is 1, but that becomes t plus y equals 1, and that becomes y equals 1 minus t. Great. Now, I just need to know what z is. So how am I going to get it?
Do you plug in y?
Not just y, but you are right. You put x equals t and y equals 1 minus t. What do you plug it into?
Into 1.
Right. It's the only guy in town, right? And so you're going to get x squared plus y squared plus z squared equals 9. I wouldn't leave it that way, because don't we want to know what z is? So let's see what we get. That guy's going to be t squared. That's going to be 1. Take away 2t plus t squared. Add z squared equals 9. Z squared then is going to be 9. Subtract 2t squared. Add a 2t, take away 1, so okay, that becomes 8. And won't z be the square root of 8, take away 2t squared plus 2t? I guess technically it should be plus and minus. Let's just assume we want the plus value. So the space curve would end up being t, 1 minus t, the square root of 8, take away 2t squared plus 2t. And you could plug that into the software and see what kind of curve it is. I'm pretty sure, because I only picked the top half, it's probably only going to be the top half of a circle, right? And then you get the bottom half. We go with the process. Make x equals t, and then use that to try and generate y and z only using t's. Now, in some cases, you're not going to make x equals t. You might make y equals t, or you might even make it z equals t. Example, suppose that you had x squared plus y squared equals 9, which, by the way, is the surface of a cylinder going vertically up the z-axis. So suppose that's my first surface, right? And my second guy was 2y plus z equals 1, which is some kind of plane. So I can imagine a plane cutting through that. I'd probably get an ellipse, right? Would be my best guess. In this particular combination, look at the equation that's the simplest to deal with, and then I would look at that guy and I would say make z equals t. Now, once I make z equals t, wouldn't I be able to figure out what y is in terms of t? And then once I know what y is in terms of t, if I go up here, won't I eventually be able to get x in terms of t? And we're done. So let's return back to the question. Okay. And I think it's here. We're being asked to find where z equals 5x squared plus y squared, which I believe is a paraboloid. Do you know a paraboloid is like a three-dimensional version of a parabola? It's like a monk's hat. You know the monk's hat, curved like this? Acorn, it's got the same kind of surface to it. And y equals 6x squared. Do you know y equals 6x squared is like a big happy face, like a gutter? And it's going along the z-axis because that's what's missing. So if I was doing this question here, which one would I decide to call t?
Y.
Any other suggestions? I mean, actually, y would work, but I think I've got a better one.
we just do Z?
No. Guess then. It must be X. So let me try and explain to you why I think X equals T is a good choice. The simplest of these two equations is the one that's only got two variables. So always focus on the two variable one. Don't focus on the three variable one. You end up going in little circles that gets you nowhere. Now, in this case here, y equals 6x squared. I think making x equals t is going to simplify the process. Because if I make x equals t, won't y be 6t squared? Agreed? So I've already got x is t, y is 6t squared. Then can I go over here and plug them in and see what we get out of it? But when I do it over here, won't z be, you know, actually it looks to me like z might be something simple like 31 z's t squareds. And we're done. I am going to criticize the textbook, and it's not just me. Question 10 is asking where two space curves meet. Okay, I take it back. We're cool. I was going to criticize them, but they're not. What they've said is totally valid. Space curve R1 looks like that. Space curve R2 is essentially a straight line. These two space curves are going to meet. Evidently, they're going to meet twice. I can imagine that. Can you imagine a straight line in 3D and then a curve hits it and then later on it hits it again, right? Curves can do that. Two straight lines can only meet at one point, but a straight line can meet up with a curve lots of different times. So here's the puzzle. What would be the method that you would use to find out where this space curve meets up with that space curve?
I would solve for t on R2 and then plug that into R1.
So what do you mean by solve? Do you mean make it equal 0 or something?
That's kind of what I was thinking. Yeah, set it equal to 0 and then solve for t, and then you can plug those values into the second one. Or the
Yeah, I'm thinking about that. Interesting idea. I don't think it would work, but it's an interesting idea. But there's a part of what you said is kind of close to what I
or
was thinking.
set them, so set the x coordinates equal to each other.
Yes, that's it. That actually will work, right? So you were on the right track. You just had to think it through. So what you do is you say, okay, I'm going to make t equals 1 plus 2t and solve. If you do that, I believe t equals -1. Okay. And then you go t squared equal to 1 plus 6t. And you'll probably find two values of t. And then you do the t cubed. Well, actually, you don't need to do the third one. Once you've done the first two, can't you just basically, hopefully you've got two values of t by then, in which case you're finished. T is 0, t is 12, you know. Whatever the small one is, put it there. Whatever the big one is, put it there. Technically, you should use the z value as a check. So let's suppose that we went back to the beginning, right? For the x's to match, t would have to equal 1 plus 2t. That means t has to be -1, right? Well, if I was doing a check, you plug in -1 here and you get the answer -1, 1, -1. And then you plug -1 in here, and shouldn't they be the same values? If they are, you do have an intersection. And then if you discover another value of t, you check it out on this fella, and then you check it out on that fella, and they both need to match. Because sometimes you can get a ghost solution. And otherwise, can you imagine that you match the y values, right? And you get t equals 5, but t equals 5 doesn't match on the z values, so in which case you can't use it. Right, Travis, you have a question. What is your question?
Is there a way to know if they don't intersect at all?
When you try and solve the question, let's just pretend that I match the x's up. And the answer that I got when I matched the x's up was t equals 5, just for argument's sake. And I plugged it in and it works for the x's, and I plugged it in and it works for the y's, but when I plugged it in, the z's didn't match, right? The z's was 22 and the other z was 44. That would be, they never meet up. Now, the reason why I was puzzled and then I thought again and decided it was right is that they're making these variables the same thing, and that's actually makes sense. Geometrically, I'm going to draw in the air here, but can you imagine that you've got a space curve and then you've got another space curve? They're like two jets flying. Can't one jet pass through the pathway of the other jet without hitting it? They're only going to meet up if the t values are the same number at the same point. I have to be here at the 5-second mark. You have to be here at the 5-second mark. Otherwise, what you get is a near miss, right? The first aircraft flies in front of you, but it's passed before you reach that point, in which case it wouldn't be a match. So yeah, you could get a number of places where that might happen. And here, they want you to put the answers in terms of the smaller x value and the larger x value. So it looks to me like this is going to have two solutions, right? Two different places where that's going to work. Hard to imagine too, but I'll assume that it is. This is winding back a little bit. Can you remember we talked about domain? So here is the domain. And, oh, good. They want interval notation. So your answer might be, you know, something like that, right? Remember interval notation, square bracket you can use me, curve bracket you can. Here's another example of finding a domain. Here's a limit. That's a cool one. Oh, goodness gracious. I should have thought about that. Okay, look at the limit, number 14. 3e to the t, take away 3 over t. If you find the limit as t equals 0, you can't plug t equals 0 into that first expression. See this one here? Because what you get is the classic indeterminate form, right? 0 over 0. Isn't that going to be a L'Hopital guy? I believe the answer is 3. But there's a guy I didn't show you because I didn't even expect them to do that to you. You see that guy there? Right. There are two ways to do this. Can you remember a weird named method called the conjugate?
Yep.
You didn't like it, you met it, right? And you probably still don't like it today, but in that question there, the conjugate method will work. And if you give me a few seconds, I'm going to show you just that piece. So if you kind of need your memory jogged.
Wouldn't
Yes.
L'Hopital's rule work too? Because if you plug in
It will.
0 over 0.
Yeah. Right now, if you plug in 0, you get 0 over 0, so L'Hopital will work. But L'Hopital, no, just L'Hopital will work, is the short answer. But L'Hopital will work in this question. There are some conjugate methods where it doesn't work. So it's worth it to show you in case the next one is. Do you know that the software is kind of clever? It randomizes some of the pieces. So that if you were doing a question and your friend George was doing a question and you phoned him up, he wouldn't be looking at the same question as you. And in this case, it looks like there's no red number, so there's no variation. But I can imagine one where there is. So I'm going to go out and in, and we're going to get your brains working on the conjugate method. Now, You could do L'Hopital on that. The answer, it would work. I believe the answer is 1, but you can double check it. But this is how the conjugate method works. You multiply this fraction by a special version of 1 called the conjugate. It's made up of these two terms, but with an add instead of a subtract one. Ringing some bells? Now, you multiply the top together and you basically leave the bottom alone. So this now becomes the limit as t tends to 0. Now, when you multiply this guy times this guy, do you see a difference of 2 squares? Now, if you FOIL it out, that'll work. It just takes you an extra line. But if you recognize that it's a difference of 2 squares, don't you get this guy squared to take away that guy squared? Which means you get 1 plus t take away 1. If you don't believe me, FOIL it out and eventually you'll get that, which simplifies down to that. We cancel the t's. And I was wrong about 1. The answer is a half. Now you can plug in 0. So that would be the conjugate method. Didn't even think they were doing it. I think because this one uses L'Hopital, I'm making a guess here that you might not ever need to use the conjugate method. Right? If they give you a square root one, they're giving you one that the conjugate method isn't necessary because L'Hopital will do the same job. Any questions? Are we good?
Can you
Cool.
put the thing back up, please?
I'll bring it back in a few moments. Just let me make sure that I've finished everything. We are, right? And so there's a little video to watch and then you say true or false. Okay, so let me get you back to that picture that you wanted. Are space curves kind of expanded versions of Math 141, you know, f of x equals x cubed? Just cleverer versions. Limits are very similar to limits, aren't they? You just do them 3 times. Intersections are match the x's, the y's, and z's essentially. Limits, L'Hopital, usual kind of techniques. If you have a space curve in 3D, and I know it's not part of this course, but it is so much fun to do it. What have I just written down?
4th dimensional space curve.
You will have a headache if you try and visualize that. Agreed? Can you see that you can expand to curves in 7 dimensions in string theory, 11 dimensions? I think it's 11 dimensions string theory works on. Can you see it doesn't matter? Because if you know how to do a 3D space curve, can't you do a 5D dimension or a 7-dimension space curve? Won't all the same properties exist? The difficulty is for human beings is that we can imagine up to 3D because we live in a 3D world and we have software that can emulate it at least. There is no real way of visualizing anything after that. Doesn't that mean then that we have to trust the math? So some shapes may not even be the same kind of shape anymore. And I'm using the word shape very loosely. I mean, what does a fourth dimensional helix even look like?
Wouldn't it just be technically the same thing as a regular helix, but the fourth dimension's just when it exists?
My guesstimate, and I'd have to go and look this up, would be that it would have a sine in it, it would have a cosine in it, it would have that, and then it would have another one. I believe the sine and the cosine are the part that generates the helix-like curvature, and that these two are just distortions in two different axes at the same time. I couldn't visualize it, but that would be my best guess at what a helix might look like.
Isn't everything already parameterized around time anyway?
Yeah, I guess I should call these U. Right. Now, I don't know, yes, when you talk about movements of object in 3D, that's why we use T, it is T. But if you travel into string theory, I don't know if string theory sees time the same way that we see time. Maybe they just see time like X, Y, Z, W, and time is just another dimension. And then there's 5 more guys after that with their own little weird letters of the alphabet. I've read some of it, it's fascinating. Do you know that we think of dimensions as being infinite, but do you know some dimensions can be finite? Which is a weird concept. In other words, in the Z, not the Z, in the W axis, you only live in a little bubble. In the W axis, it only lives from 0 to 1. Right? The values that you take in that dimension are quite restricted. So there is some weird stuff going on in that part of the world. And sorry for distracting you, but I thought that was kind of cool. That we can now emulate moving objects in any dimension you like. And we can even have them meet up with surfaces in 4 dimensions. Right, do you know how you've got the surface of a cube in 3 dimensions? Do you know a thing called a hypercube, which is a 4th dimensional cube? We could have a 4th dimensional space curve intersecting with a hypercube. It's kind of weird. Right.
Sounds like something you'd use to plot the course of the TARDIS.
Ah, yeah. One of my favorite sci-fi shows, Doctor Who. If you don't know it, you lot should watch Doctor Who. The old Doctor Who is ridiculously bad, but it's so bad, it's good. Right? It was made on a shoestring and things wobble and nothing. And their idea of special effects is you switch the lights out and you flash a torch. You know, it's really very crude, but it's so much fun. And I like the new one. I haven't seen the new female Doctor Who. I was keeping that to the summer break. So has anybody watched this, the new Doctor Who, the woman?
Yeah, she's awesome.
Awesome. Awesome is, yep, great. So
Yep.
I'm looking forward to seeing her.
Yeah, actually, my youngest daughter is named Clara because we're such big fans.
Cool. Oh, if you ever come, I know we can't do it. If you ever come by my office, I have got some cool Doctor Who stuff that you may want to see, right? So even if you're not a student, right, drop by when we're back to being human beings again, and I'll show you some of my cool things. When I was back home in Scotland one year, they had a Doctor Who exhibition, and I actually went, and that's where I bought some of the stuff. So it's really fun. And I'm distracting myself. I knew it. I apologize. Let's look at the calculus of space curves.
Professor?
Yes?
I just had one more thought. I've heard a 3-dimensional cube.
Yeah.
Is the shadow of a 4-dimensional hypercube.
That's one way of looking at it. Yes, a shadow. This is a version that I've seen that kind of makes is obvious. This is meant to be a 3-dimensional cube, right? Now, on a cube, it's got 6 faces. If you take a cube and you break it apart, you make what's called its net. So can you imagine folding this back up? It would make a cube, right? This is called the net of a cube. And this basically here is the 6 faces. You imagine you cut it across a couple of the edges and you flattened it out, right? If you bent it back up and sellotaped it, wouldn't it become the cube again, right? A hypercube says that each one of these is a cube. So the net of a hypercube is a shape that looks like this, but these are not squares. These are all 3-dimensional cubes. So can you imagine what's happening is that the cube is folding into itself. And you are allowed in dimensions to occupy the same space in a different dimension, which is kind of weird. So I like that. I like that version of what a hypercube was.
And
Okay.
if you were to do that with the hypercube, make the net, is the next dimension up just another cube on
where
the
each
cube
of its
the cube?
faces are hypercubes.
Oh my god.
Oh God, I think I've put a bad thought into your brain. You're going to have nightmares now. Do not try and visualize anything after 3 dimensions. Trust me, it's not a good place to be. Okay, let's look at calculus of space curves. When I mean calculus of it, I mean, how do you differentiate space curves? How do you integrate space curves? Notation is good. You call it R dash T or dr by dt. That's notation.
You just integrate each part of, like, so if each coordinate's a separate function, when you just integrate each function by itself?
Or differentiate, yes.
Or differentiate, yeah.
Yeah. So isn't that so intuitive and so nice? If you want to differentiate a space curve, just differentiate totally independent of each other the x, the y, and the z functions. So, for instance, suppose I take a helix. That's one of those helixes that gets bigger. And can you see it's going to go vertically upwards? If you want to get its derivative, you differentiate sine, which is cosine. You differentiate cosine, which is sine. And you differentiate this guy, and you get 4t. Is that, there is something elegant about that, isn't there? You can imagine it could have been something really ugly, like some kind of weird cross-producty thing that you then done something else to, or some kind of, you had to combine the 3 in some weird product stroke quotient rule or something, you know. It could have been so ugly. But it was so elegant. Isn't that really cool? Now, what is the derivative of space curve telling me? That's actually quite fascinating as well. So let me go back a little bit to the 2D world. Do you know sometimes in Calc 1, we would call the function, instead of f of x, we'd call it s of t, and it would be t squared plus t plus 1. It'd be something like that. Remember doing those things? And we would find its derivative, but when it was written this way, wasn't this the basic displacement time, right? What was the definition of a derivative?
The derivative was the instantaneous slope at any point.
That is correct. And wasn't it also the velocity?
Yeah. So like the derivative of a position function would be velocity. The
Yes.
second derivative would be acceleration.
You're right on top of it. So when you take a space curve and you find its first derivative, you are finding its velocity function. We typically call it v with the arrow, right, to make it a velocity. And if you want to find its second derivative, and you, in this case, you would what, negative sine t cosine t and 4, right? You would get its what is called its acceleration vector. Doesn't that match really nicely with what you did in Calc 1? That's kind of cool, isn't it? It's not too distracting. Now, visually, what does that mean, velocity function? Because it's a velocity vector. It's not a single number. It's not like in here you get the answer 10 meters a second. So it means at that exact point in time, the instantaneous velocity was 10 meters per second. So if you were in the car and you looked at your speedometer, that's, you know, that would basically tell you what you were going at any given moment in time. So I want you to imagine that, I know this isn't a helix, but let's pretend it's this guy here is our space curve. And I chose a point here. And let's say that point is t equals 3. If you take that point and you get its derivative, you get a vector v that looks like that. So can you imagine I took this guy and I plugged in 3, whatever the cosine of 3 is, sine of 3, comma 12. Can you see that that would be the vector? Here's one way to visualize it. I like this way anyway. Maybe it's because I'm Scottish. Can you think of a space curve as being a really funny roller coaster? Right? And can you imagine at this point here, the roller coaster is broken. And when you get to it, you shoot off to your death. The vector, as you shoot off the roller coaster, right? That arrow that's saying, ah, right? That is your velocity vector. That's what your first derivative vector looks like. Can you see it's kind of the direction that the curve is pointing at that point? Wouldn't that be the direction you'd shoot off before gravity took over? I kind of like that analogy, right? So velocity is the direction you'd shoot off a roller coaster to your death at. It's the direction of the space curve at any given point on its life t. That makes sense. Now, there are a lot of similarities between what happened in Calc 1 world, right, and what's now going to happen in Calc 3 world, right? 2-dimensional, 3-dimensional. But not everything follows. I'll show you what I'm getting at. In the 2D world, didn't we have things called local maximums and local minimums? Right? And we orientated things with the x-axis as being naturally the horizontal axis, right? And we always thought of the y-axis as being vertical. And local max and mins are the tops of hills, right? You cannot talk about derivatives being 0. Because essentially, at that point there, wasn't the derivative 0? Isn't that, in fact, how we found out where those places are? Because the first derivative is a vector, do you see that you don't typically get one thing? Don't you typically get 3 things? It means that local max and local min don't have the same meaning, or even do we try and look for them typically. Now, some people, I'm probably one of them, would think, well, can't we just change the rules a little bit? And can't we think of Z as being vertical? And so the local maximum would be the place where the curve got to its highest. And in some senses, that's correct. But we don't tend to do that. And here's the answer. Do you know X, Y, and Z are the 3 dimensions of a point in 3D space? Imagine you're in outer space. Is there any direction that's up compared to any of the other 2?
No.
There is no natural up. Couldn't X just be as up as any one of the other three? In fact, up is probably not a concept that you should use in space, right? When the guys were in their Apollo spaceships, they never said, "Oh, we're flying upwards," right? I mean,
Incidentally, there's no origin either.
correct. There is no origin, which is kind of weird. But we tend to get round that problem by creating our own origin. And so I'm making this up because I'm not into physics, but I would probably pick the sun as the origin. That seems reasonable, at least for interplanetary movements. You might change that to the Milky Way center if you were going to do intergalactic movement. Right? You need an origin, right? Because you need an origin to create space curves, right? You need to have some place to say this is the start. Right? But you're right, there is no real origin. Although I believe there's a place in America that said, there's a little town in America, look it up, that says that they are the center of the universe. Because you know there's no center to the universe either. There's no origin. And since anywhere can be the center of the universe, that town got in first and said, we're it.
Wallace, Idaho, by the way.
Oh, someone knows the answer. I didn't know it. It's Wallace, Idaho.
Well, I just looked it up. So the answer is Google, as in all things.
Yes. So there you go. So that was quite an interesting thing. Do we have time? I think we do, yes. We're going to do a lot of practice at this. So it's going to feel a lot like Calc 1 in very many respects. You know, find the derivative, find the second derivative, all that kind of fun stuff. Here is another space curve. I'm keeping them nice and easy. If I was being asked to find the velocity vector, wouldn't I just say, oh, you mean the first derivative? In which case I would get 1, 2, 8t. Now, sometimes you're asked to find that guy. Now, isn't that guy the magnitude of a vector, right? The length of a vector. So it would be the magnitude of this guy. Well, to get the magnitude, don't you take the x component and square it? Don't you take the y component and square it? And don't you take the z component and square it? And so you end up with 64t squared plus 5. If the derivative, the first derivative, is the velocity vector, what meaning do you think the magnitude of the velocity vector is?
That would just give you, well, the velocity is the vector. That would be the magnitude of the vector.
And
Speed.
yes. Remember my story about the thing, the shooting off to your death? If you calculate the magnitude of the vector that you shoot off to your death, that's the speed at which you leave the roller coaster. I'm going to shoot off to my death at 40 miles an hour. I'm going to shoot off to my death at 4 miles an hour. I'm still going to die, right? But one, I'm going to go faster as I shoot off, and another, I'm going to go a little bit slower, but I'm still going to fall off the edge eventually. Does that kind of make sense? In fact, when you talk about 3D, doesn't the difference between velocity and speed become much more separate? They're quite different entities. Isn't speed going to be a number? You know, if I went and said, what's my speed at time 1? Won't it be the square root of 69? What's my speed at time 0? Isn't it going to be the square root of 5? Do you see it's a scalar? But won't my velocity at speed 1 be 1, 2, 3? And my velocity at, my velocity at time 0 is 1, 2, 3, and my velocity at time 10 is 5, 6, minus 2. Do you see that velocities are vectors? Velocity has a magnitude and direction. Speed is only the magnitude part of it. And we're doing really good, Tim. I didn't think we'd get as much as this covered. I should pause for a minute. We're going to do examples of this, but as the idea of magnitude of velocity and how you might calculate it make sense to you? Can you imagine doing it in situations? Sometimes it's going to have t's in it. If I tell you what t is, it becomes a pure number. Here's another space curve. I wonder what integrating a space curve looks like. How do you do it?
Same way as deriving, just each one by itself. So 1/2 t squared e of t, and then negative or positive cosine. I can't think right now.
It's negative. Oh, God, I'm saying it's, yes, it is negative. Oh, no, it's been a while since you may have just integrated a simple thing like t, but since this is a general integral, don't you have to do a plus c?
Yeah, I just realized I forgot that.
Yeah, that's fine. You did good. And here's the problem. You can't use the same c. Isn't c an arbitrary unknown constant? And aren't each one of these totally separate from each other and have no interaction with each other? So
yes,
you call
they
this,
could be completely different.
right, so you call them C1, C2, C3. Right, C1, the arbitrary constant for the first one. So you might rewrite this answer in two pieces just to make it easier to see. The algebra bit plus C1, C2, C3. Now, what on earth is that? Well, it's a vector. Now, we know from Calc 1, or Calc 2, I should say, isn't an integral, one way of looking at an integral, isn't it the area under a curve?
Yes.
Yeah.
So would this be the volume towards the origin or towards the center of the shape?
The volume's a different thing, so I wouldn't go that way. But area under a curve is very common. And that doesn't make sense here, because that's a vector. How can a vector be an area? Isn't an area a scalar thing? You know, volume is a scalar thing, right? It's a single number. And so interpreting the integral in this case doesn't make sense to think of it as an area under a space curve, because there is no under, right? Remember, z is no more up than x or y, right? So that kind of loses its meaning. It's actually got a really unusual meaning. And it doesn't actually, for the most part anyway, it doesn't actually get used much. You know, we do an awful lot of integration in the Calc 2 world, right? There's a whole Calc 2 to do with integrating, right? And how you can do it. But in the Calc 3 world, integration is quite a minor player. It doesn't get used much. Yes, Travis, what's your question?
Would it be the distance that you traveled?
Interesting thought. No, but I could imagine why you would think that. That we are going to find how to calculate that, but no, not directly. Here goes. I want you to imagine that t equals a, you were here on space curve, and at t equals b, you finished there, right? And can you imagine that we got the integral from a to b of this space curve? So these C1s and C2s and C3s would disappear, right? Wouldn't you just plug in x, t equals b, t equals a? And let's just say, for argument's sake, that the answer that we got was 1, 2, 3. It's a vector, as all integrals will be, right?
Is that the vector that would connect A to B?
That would be so cool, wouldn't it? It's not, but it should be,
okay.
right?
Yeah.
In a nice world, it would be that. But it's not that far away from what you're saying. Can you imagine that at every given point, there's a direction to this vector, or this space curve?
I'm just taking the shotgun style, trying to.
Hey,
Ideas
this is how mathematicians think of things. You come across a new problem and you just brainstorm it, and 3/4 of them are stupid, and 1/4, and they are when I do it, and 1/4 of them are, hey, that might work. And one of those 1/4 is probably the answer you're looking for, right? So you kind of say, I wonder if it's just A to B. I'll try it out and find out. Oh, darn it, it's not the same answer. Okay, it could have been. And do you know if it was, you say, hey, we now know what it is, right? So that's how you would do it. What it is, can you imagine all these different vectors? Do you know that the average of them?
The average would be the magnitude of the integral?
No, it would be this
Or
vector.
just- it'd just be the
Right, so
vector?
you imagine this one's 1, 2, 4, and then this one's 7, 8, 9, and this one's 1, 42, minus 3, and this one. Can you imagine adding all those, or combining them, maybe a better word, right? Adding them or combining them. Can you imagine that the average of them would be pointing in that direction?
All right, that makes a little bit of sense. Still a little, seems a little odd, but
It's almost like the average from here to here, but can you imagine that the average from here to here might not be the same thing as what I just described? How could you use that? Well, here's a made up one. I don't think they're doing it. Can you imagine that there was an aircraft and you were watching it on radar and you detected its pathway? And the aircraft is trying to confuse the enemy about where it's heading. So if you're flying, it's probably not a good idea to keep flying in a straight line. Isn't that going to make it easy to shoot you down? Right? You're going to, and you also don't want the opposition to know which city you're trying to fly to or which location you're trying to fly to. So you do zigzags. If you model this space curve and you know this guy and you know this guy, right? So you started on the radar at time 0 and you finished looking at it, say, at time 10. If you average this out, won't this basically tell you that he's flying in that direction? And therefore, if you continue that direction, won't you have a good idea where he's trying to go to? Even although he is zigzagging, isn't his zigzagging only a cover for, you can't zigzag away from the place you're trying to get to, right? Because then you'll never get to it, right? So you do have to have an underlying direction that you're trying to disguise by zigging and zagging.
So they can like approximate their bearing?
Yes. And that gives you an opportunity to send other aircraft out to intercept it. It also gives you opportunity if you project where that direction would land to. Oh, that looks like it's going for Chicago. Okay, Chicago, bad guy coming, right? You can imagine that. I like military things, so I do military analogy.